Yeah, so we assume we have we have two presentations today, but if you would like to present what you prepared, then please let us know via the chat screen. All right, so please proceed.
A moment, please. Can you see my monitors on my display? My note? Oh,
We
yes.
cannot see your notes. All I can see is you share your tablet, but that's it. No shared content.
Oh, one moment. Oh, mm, I I rehearsed this, but why don't? One moment. Mm,
Take your time.
In so this is not screen share. You can find the screen share button in the top. Think this triangle button maybe.
yeah,
This yeah, yes, maybe. Then you can, yeah, this smart view.
yeah. I did,
And,
but
and then you can find another application.
another
Some
application.
Flow have two uh, functions. One
Yes.
is chat and this chat. Yeah.
Oh,
So
okay, one moment.
there should be one more application
Oh,
in your um, PC.
ah, this one.
Yes.
What about now? No?
Uh,
Oh, I'm sorry.
now I can see your screen.
Oh, it works now?
Yeah.
Oh, I'm sorry. Yeah, thank you. So today, my presentation is about the connection between the integrals and topology by calculating the integrals of one form on a vector field, and by computation these integrals for S1 and S2 and T2. So let's dive in. So the first one, so we're gonna learn about the vector fields and we learned about the vector fields and one forms. And so in R2, just regular standard coordinates, x comma y, the Euclidean metric is dx squared is dx squared plus dy squared. And then if we have a vector field v and tangent vector u, then we write as a vector field as like this p times s partial derivative with respect to x, and then q with y, and then tangent vector u is like this way as these are basis tangent vector.
It's slightly wrong in the following sense. So of course the coefficients are different. The tangent vector level, the coefficient should be scalars. That's fine. And for V, the vector field also, as you pointed out, the coefficients are the functions of x and y. That's also okay. But
Yes.
also the meaning of the ddx, ddy is are completely different. So in the vector field level, we didn't fix the point to take the derivative, whereas for the tangent vector, so the point is already fixed.
The point
So,
is already
so that you
fixed.
should like to specify on you that so which point we'd like to differentiate. Whereas for the vector field, we should not fix the point. That's also important difference.
Yeah, actually, during this preparation, I changed the my attitude and the style. So let's just go on, move on, and I'm gonna explain later. So yes, and we have two orthonormal bases, the partial derivative with respect to x and y, and then we're gonna define the new function as an inner product, v and u. And this is orthonormal basis. So v and u inner product, their inner product is going to be just by linearity. If we expand like this way, then these bases are orthogonal. So this is going to be canceled out as 0. So we have this equation as this function. So alpha v of u is p times a plus q times b. And then if we have the dx of u, and then dx, the u was like as defined as this way. So we have dxa with partial with respect to x, gonna be a, and dy, we gonna have b. So we're gonna substitute these into this start equation over here. Then we have this one form. So the one form alpha of V is the covector field from V by flat. This is musical isomorphism, but I didn't like go through deeper yet. Okay, just let's move on. I'm gonna just have some computation through this example. So the first simple example, if we have V as minus y partial with x times partial y, and then we can use these functions definitions. So alpha of u is inner product v and u. According to like in this definition, we add this result and this result. We have this result like p times dx, and this time p is minus y, this one, and the q is x, so times dy. So this is one form, and I'm gonna go to the next step. Oh, I'm sorry. So I'm gonna look at the line integrals as integrals of one forms. So if we had curve gamma of t is x comma t and y comma t, t from A to B be smooth. So we have smooth function. The line integral, as we learned in multivariate calculus, so the line integral of v along r is defined as like this one. And then this is the equivalent to each other. So we can use the multivariate chain rule, and we can get the value of this integral as like this expression. And then there's a one concept of pullback. So I didn't study deeper yet. Okay, then I just at that time I just keep this in mind, this concept. And then the chain rule is d of x of t is x prime t times dt. And in the similarly, d of yt is y prime t and dt. So this new notation, r star alpha is p of x of t, y of t times x prime t dt and q times y prime t dt. So if we had the not this is line integral. If we have this alpha, if we have this integral, then we have this result and the substitute, and this one is the same. So the vector field line integrals are one form integrals, which means this alpha is one form. What does this mean? So I'm gonna show you the computation with the example S1, which is unit circle. So on the 2D plane, we have unit circle over here. Then so we have a curve, smooth curve, gamma of t is defined as cosine t, comma, sine of t, and the t from 0 to 2 pi. And let V be a vector field, which this one is called the rotation vector field, as far as I know. Then the first one, the one form, alpha of B. By the way, this is not like the subscript as a partial derivative, just like a notation. This came from vector field B. So just this one form alpha is minus y times dx plus x times dy. Because if the vector field is P and Q, then we had a result, P times dx, the Q times dy. So we have two methods. The first perspective is the vector field in line integral. So this is just a regular vector field line integral. So we can get the derivative of r gamma of t. So cosine t is derivative is minus sine t, and sine t is cosine t. And then v of gamma of t is, we can just substitute minus y. So minus y, this one, minus sine t, and x is cosine t. And then using the multivariable chain rule, so v of gamma of t times gamma prime of t is, you can just simplify the inner product, and then sine square of t and cosine square of t is equals 1. Therefore, the line integral on the vector field line integral is from t from 0 to 2 pi. just V of gamma t times gamma of t and dt. And we had just 1 as above. So integral of 0 to 2 pi dt, which means it's just 2 pi. What about using one form integral? So as defined, x of t is cosine t, y of t is sine t. So we can get the d of xt and d of yt as you see this. And the one form alpha is minus y times dx plus x times dy. So you can just substitute. We have this one, and then this one, gamma star alpha v, and then just times, and we do the computation, just you can just do this. And then this integral also of one form is 0 to 2 pi in the dt. So which means just 2 pi. As above, we have the value of 2 pi in the line integral. At this one form integral, we have the same value. At this point, I had a Dr. Cho's feedback. So we can distinguish the topological differences of S1 and S2 and T2. FYI, this T2 is real embedded, standard real embedded torus in R3 by observing how the integrals associated with this just same vector field or just this one form minus y times dx plus x dy. And we can check via Green's theorem and Stokes theorem. Okay, so I'm going to show you the first case is S1 via Green's theorem, and the second case is S2 using Stokes theorem. By the way, which means the Stokes theorem, there are two versions. The first one is just classical Stokes theorem, and the other one is generalized Stokes theorem. And third one is just torus real embedded R3 using Stokes theorem. And what was my observation? It's going to be the last part. So let's move on. The first case, so S1 using Green's theorem. Just recall this Green theorem as we learned in calculus course. So if we have just like this region's integral, this part is called 2D curve. And it's the same as the vector field line integral. That was Green's theorem. And so let's define the unit disk, which means it's not just circle. We need a reason. So we have this part as a reason as open, not closed disk, unit disk, like this way. And we have the same vector field as above. And then Green's theorem was like this one. And this part, we already know that P is minus Y, Q was X. So you can just substitute in this one. And this part is 2D part. So we can just, compute. So Q was X. So partial X with partial X, just 1. In the same way, this one is minus 1. Minus minus the plus. And it became 2. And this part is just literally the area of the unit circle. So we have 2 pi. Oh, this is the same value as above. That was I was shocked and it was fun. What about Green's theorem? And is there another method? So I just tried to this one, Green's theorem as 2D version of generalized Stokes theorem. So the generalized Stokes theorem, as far as I know, like this way. So if we have integral of curly d of omega, this in here, this omega means one form. In here, yeah. And then this omega becomes d omega, and then this boundary becomes d. It looks like opposite operation. Okay, interesting. And then if we look at the Green's theorem as this perspective, then we can look this one is this way. So this boundary is going to become like this way. Okay, then let's compute. On the same setting, you have a unit disk and same vector field. Its boundary is a unit circle. This part, yeah, this boundary, that is curly D is S1. And then for convenience, I'm gonna just write alpha instead of alpha of B. So this alpha, one form was this one. We already, got this. And then we need D alpha because we need this part, D omega. So we need this part, D alpha. Then how can I get this D alpha? So at this point, the new concept was arised, the exterior derivative. But I'm gonna put aside the details later. So I'm gonna just compute. So D alpha is like we can just think of this exterior derivative is vector. So by linearity, it's D alpha. So alpha was this one. We can just distribute. You can just expand with edge product. D of minus y dx plus x dy became this part is d of minus y wedge d of no dx. Yeah, this part. Like in between this wedge product, like it looks like this way. Okay, and then this scalar multiplication minus one, we can factor out this part. So this part is very important. This is the property of wedge product. If we just the product is anti-commutativity or anti-symmetry, which means we can just commute. Like dy times dx is going to be same as like if we just like think of just some numbers, a times b and b times a, commutative, but not the wedge product. So by definition, if you just swap each other, then the negative sign is going to come out. So negative becomes plus. So dx wedge plus dy plus dxg plus dy, which means these are the same, two forms. So we have two dx wedge dy. So we can apply a Green's theorem now. The first one, so we are doing the integrals on the boundary S1, this one form. So this boundary was Pauli D. And then this was generalized Stokes theorem in perspective. So alpha gonna be D alpha, and the Pauli D gonna be D. Unit disk. So this unit disk D on the boundary, we had D alpha as 2 times dx dy. And then we can factor out 2 out of this. This is just it's the same as earlier, just the area. So we have 2 pi, which means it's the same value.
I have a question.
Yes.
Can I ask something? So one question.
Yeah.
Okay. You said the alpha is. You said the exterior product
It's their derivative.
has the
Exterior product. Which
Extent,
product?
yeah, wedge product. Yeah, this one
Yes,
wedge product. Yeah,
has the property anti-commutativity.
yeah,
So d alpha is 2dx wedge dy now,
yes.
but it is equal to minus 2 dy dx, right?
Minus, yeah, minus 2y dy, yeah, wedge dx.
So
Yes.
when I put
Oh,
d alpha in the integral,
oh, yes.
then
Oh,
I
yes.
think I will get minus 2 pi rather than 2 pi.
Oh, oh, that's a very good observation. Yeah.
So what happened? That is my question.
Oh, yeah. Actually, I just learned this concept just for the first time. So, yeah. I can't answer the question right now yet. Oh, but that was very, yeah, good point. Yeah.
It just
Oh,
depends on the so-called the orientation. So the generalized
oh,
Stokes theorem uses the orientable
oh,
assumption.
oh,
So
oh, yes.
orientability changes the sign. So
Oh, that makes sense. Oh, thank you. Oh. Any other questions so far? Okay, then let's move on the second case. So we're gonna do the integral on S2 using Stokes theorem, which means the first one is just classical Stokes theorem in multivariate calculus. So we can just recall this one is Stokes theorem like this way. So we have unit normal vector usually in convention outward, but I think just it depends on the situation. Yeah. So for now, for this presentation, I'm gonna use the unit normal as outward using unit normal vector. So we need expand to apply Stokes theorem. So let S be the upper hemisphere of the unit sphere. So if we have just unit sphere S2 in R3, then I'm gonna just integral over upper half hemisphere. So we have S defined as just hemisphere, just upper half hemisphere. Yeah. So we have same vector field, but this is R3. So I'm gonna set the Z coordinate as 0. Oh, by the way, this notation means just vector notation, not the inner product. Yeah. And then we need cross product or curl of F. Then we can just compute the cross product. So we can get 0, 0, 2 as a curve. Then the classical Stokes theorem, this line integral is this one, is the same. We have this unit normal vector as 0, 0, 1, y. I'm gonna just use the outward unit normal vector. So if I'm gonna end the one more thing the one more important thing that is in Stokes theorem, it tells that it doesn't matter what surface I'm gonna take. So I'm gonna just instead of this sphere, I'm gonna just take this on the xy plane, just unit circle. Then I'm gonna just have this unit normal vector, just like without computation 0, 0, 1, because it's outward. And then as simple just calculation. So on the unit circle, just this one is area, just 2 pi. It's the same. What about generalized Stokes theorem? So this one. So we need d alpha. So alpha was defined in R2, so we can just expand. So put the z coordinate as 0, then it's going to be the same. The remaining part is going to be the same. So on the same setting, just boundary was just curly S is S1, which means unit circle, this one, this curve. And using generalized Stokes theorem, and at this point, I'm going to use spherical coordinates for parameterization. So this part, I believe we already know this, parameterization. So I'm going to skip this. Then we can just, of course, get the dx and dy as a definition in the multivariate calculus. The partial partial x, partial phi times d phi, partial x, partial with respect to theta and d theta. So we have this one and this one. And this is I'm not sure if this is okay. This is just my personal lecture, personal notes. So I use this shorthand notation, but I'm not gonna use this on the formal seminar or anywhere else. So I'm gonna denote S as sine and C as cosine. It's too too long. The expression is too long. So this part we're gonna do we're gonna do wedge product dx wedge and dy. We have this one dx. Substitute this into here, into there. So this is the moment. And what is the wedge product? So what is the wedge product? As you might notice already, so this presentation is like backward. So usually I used to build up the theorems and definitions first, and then we move on to the example next. But at this time, the trial was different, backward. So the focus on the concrete example first, and then which part I need a definition or axioms or theorems. So this part, I need what is the wedge product? I need to study this part. So what is the wedge product? As far as I know, this is definition. Why? Earlier, as Dr. Cho said, is oriented. I think it's related about orientation. So this part is anti-symmetry or anti-commutativity. So if we swap together, then this negative sign come out. And then we can induce dx wedge is dx equals 0. Why? From this definition, dx wedge dy is negative dy wedge dx. Just substitute dy as dx. And then dx wedge dx is negative dx wedge dx. By linearity, we can just, these are the same, two forms. So 2 dx wedge dx equals 0, then dx wedge dx is 0. Okay. Then let's get back to the example. So dx wedge dy, as you see, the expression is too long. So I'm gonna just distinguish it with using some colors, for readability. Yes, this wedge product. So I'm gonna just expand to this one wedge, and this term is the wedge, and this term and with wedge and with wedge like this way. And then we can use this part, this property, dx wedge dx equals 0. So if you see any two same, this d phi or d theta just gonna be 0. And what about this part? Okay, we can use the anti-symmetry. So I'm gonna just put d phi first. Then this term is remained. This one is gonna become oh, the thing I already did over here. Yes. So we have this result. By the way, this computation part was too long. So I just looked it up. Is there another way? I found the note provided by Dr. Cho. We can just think of we can just get a just basic formula like or basic result, the wedge product, like a dx plus b dy, which c dx dy as like this determinant dx dy, a b on the first row, c d, like this way. So let's prove this one. We're gonna just expand using the property of wedge product, the cancel, dx dx cancel, dy dy cancel, we know that. So this part. And this one, dy dx negative sign by definition or by property. And then dx wedge dy is the common. So if you factor out 80 minus bc, a times d minus b times c, this is the same as determinant of matrix. This was very interesting. Okay, so I'm going to apply this result for this star equation again. Let's see which one is simpler. So this one, wedge this one. So this part A, B, C, D. A, B, C, D. And D phi wedge D theta. Yeah, of course, dot, dot. And then you have common, we can just common factor out sine phi times cosine phi, sine phi, cosine phi, sine phi, cosine phi. The others, cosine ze곱 theta, sine, sorry, cosine squared theta and sine squared theta is going to be 1. So we have this result. As you see, it's way simpler. So what was the Stokes theorem? The value, this one, we have this d alpha and d 2 times dx which dy. And then this part, we had this result, substitute this way. And then this step, this moment, how can I compute this? This one is out of the blue. Because how do I compute this? So we need a surface area forms. This moment we need. So I'm gonna just put it aside. Anyway, so this is gonna be just yeah. I'm gonna just put aside this part right now. What is the surface area forms? So if we have this parameterization in R3, the tangent vectors x of partial u and partial b, the area is, we usually denote dA is equals this x of u, x partial u cross product. This is outer product. X of partial v is, this is determinant or absolute value, and du dv. And the surface area form, if we call that omega of s, then it became this one. Why? Just geometrically, we can just think about it. If we have just one point, we have this way two tangent vectors. So as you know that this one means the area of this parallelogram. So this one becomes this way, right? This parallelogram, du dv, just we're gonna just think of as like a scalar. So for unit square, we gonna need this part. So partial with respect to phi, yeah, we can do this. I've done this like so many times, and I believe you had the same result. And you already know the process. And this one, so we have this result, which means partial p of x, partial theta, the absolute value is defined the area of parallelogram, but they're orthogonal. So it becomes just a rectangular, just area of a rectangle. So just this length times this length, which means x partial phi times x partial theta. And we have this one sine squared. So 1 became 1, just sine squared became sine theta. And as far, I think as you might notice that I didn't put an absolute value here, which means it's called signed area. So it depends on the orientation this indicates. So we have a result, or the standard area form on unit square is sine phi times d phi wedge d theta, or they are just the area. So using the generalized Stokes theorem, it became this one this way. So we can use the area form as this one, and we have 4 pi because it's a unit sphere. And let's get back to the earlier over here. So this means the unit area, surface area, but we consider as just hemisphere, right? So just whole just unit sphere of surface area times just 2, and we have 2 pi as the same value. Okay. Oh, I'm sorry. And then what about torus, real embedded in R3? I'm going to use the Stokes theorem. So classical, Stokes theorem, as we already saw earlier, and the parameterization, we've done this computation, so many times. I'm gonna I think I can omit this part. In this part, I think it's important. So we have unit normal vector as cosine of u times cosine of v, cosine of u times sine of v, and sine of u. The curl of this vector field f, or we already had this value earlier example, right? So this inner product between the curl of f dot unit normal vector, this x and y component are 0. So cancel out just 2 times sine of u. So the area form was this way. And we had this value already. So just substitute into this.
I have a
Yeah.
question.
Yes.
I missed the definition of the vector field F.
It was
Can you
just
draw the
minus
this?
y, x, and 0.
Ah,
Yes. Yeah.
so
We are doing on the same setting. This was minus y, comma x was on the at the beginning of the unit circle. And then we did this on unit sphere, right? And this time we're applying on torus, yeah, on the same vector field. Minus
but
y, x,
minus y, x, and 0
yeah.
is uh, you can define on the torus or uh, uh, for can you draw the F? Y- I cannot imagine where F is.
Oh, rotation. This vector field is rotation like counterclockwise. But um, you meant how can I draw this vector field on torus? Uh, the vector field was minus y and comma x and 0. So I think just like they rotate on the counterclockwise, but like this on the flat plane.
I just wonder why this
Yes.
integral should be zero. I
Uh,
think one
yes. Yes.
I can follow the
Mm-hmm.
computation by your note.
Mm-hmm.
Okay.
This
Uh,
result
yes, but
or this part or
yeah,
this whole part. I didn't explain this part yet.
yes,
Uh,
I should think. Well,
okay. So yeah, actually, I realized that after this computation, there, I I think I wasn't sure that I did this 100% correct. And the then it hit me that I should have just like fixed the angle, the poloidal angle, just 0, like this part just 0. Then I'm gonna just have this integral just only this, so this most outermost this circle. But yeah, as you point out, so I didn't do that way. So yeah, I'm gonna do that computation later. And this part we had already this result, so substitute this one, and this part is just like simple. So the integral interval is from 0 to 2 pi and then 0 to 2 pi. Just if you just think about it, this sign, the variable is u in the variable is u, this part, this first term, and du and from 0 to 2 pi is 0. We already know that, right? So we can just cancel out. You don't need a computation. What about this part? As you know, the sine u times cosine u, you can just simply sine 2u. And then, so this part, I thought I can just cancel out 0. So 0 plus 0 is 0. Yes. Any other questions? And can I use wedge product? So as a second method. And then this part as the same as earlier. And now we can compute this wedge product using this determinant. So this one going this way, this one going this way. Boom, boom. So I believe, yeah, we can just compute this way. This computation is just nothing but, yeah. So we have the same value. From the classical Stokes theorem, or we can use this wedge product as a area form, surface area. So the observation was that through these calculations for S1 and S2, we have the same value, which was two times pi. But we have different value for torus as 0. So which means the torus, why is that? The torus, so unit sphere, no, okay, I'm sorry. Let's just think about the basic one first. Unit circle has no hole at all. And unit sphere has no hole too. So we have the same value, 2 pi. But torus, what about torus? As you already know, we have one hole, or referred to as genus, as Z, and G. So for unit circle at unit sphere has no genus. For torus has genus 1. So we can distinguish the topological differences using the integral. So this was my conclusion. Thank you for your time, and any questions?
Yeah, I'd like to see the questions from the participants first. There are so many errors, so I am wondering, participant can point out.
Okay, I can learn through that errors. Yeah. Please point out the errors that are made. I'm prepared to learn. But one thing that I came to mind is that the Rocky point out that how can I do this torus, right? I think that's a point, too. Oh, yeah. Any other questions or point out?
So then let me provide the feedback
Yes.
for each. So
Yes.
first, I really appreciate what you put the effort, indeed.
Yes.
So I really like the way you learn mathematics in a way that even you don't feel completely comfortable with the objects that you are computing, but still try to go over the computation in each. And I
Yes.
know it like give you some tension for a
Yes.
moment. I definitely understand how that feels, but this is the way to learn through the computation. So that
Yes.
so even I said so there are certain errors, but
Yes.
instead of providing certain interpretation, you can really see why it could be wrong. Because
Mm,
from the quantities, I mean the values that you can see that if the logic is correct, then the value should be unique. But if you get the wrong value, then you
mm,
can see why we need to fix it.
mm,
So it's not the matter of the interpretation, but the matter of doing
yes.
mathematics. So in that way, I really love it. So let's just look at each page one by one. So if
Yes.
you go back to the first page, so over here, so can you just make the screen in a way that we can see the entire page together?
Entire page.
Mhm.
Uh,
For each page. So I'd like to look at the first page entirely.
One moment. Yes.
Yeah, this should be good. So as I pointed out, it is very important to distinguish in the notation level for the vector field and the tangent vector.
Mm.
So for you, so that you should like to point it out. So ddx and ddy for the tangent vector, you should specify the point to take the derivative.
Oh.
You understand my point? If you
Can you
don't,
repeat one more time? Yeah.
so you should distinguish in the notation level for the
Yes.
for vector fields and tangent vectors, especially. So the for v ddx ddy represent the vector fields, whereas on u ddx and ddy represent the tangent vectors. So
Oh.
that for the tangent vectors, you should specify the point to take the derivative ddx and ddy, which point you'd like to take the derivative. That was already fixed as long as you use the term of the tangent vector, whereas the vector field, you should not fix the point to take the derivative. So that in the notation level, you should say on u, a times ddx, we usually use we specify which point we take the derivative, say p, like that.
Ah, yeah.
So this is important, like the distinction that you should specify. Otherwise, the meaning is completely different.
Yes. Yes.
And all of your computation that you did is not in terms of the tangent vectors, but you did everything in terms of vector fields, by the way.
Oh. Mm.
And algebraically speaking, so for dealing with you are using the vector space structures so that you are doing linear algebra. Whereas for V, because the coefficients that you are using is not the scalars. These are
Yes.
the functions.
Yes.
So that you are using the so-called module structure rather than the vector space structure. The module
Oh.
structure means so there's a ring that should be taken as a scalar multiplication. So the set of the functions are now considered as a ring so that is used for the scalar multiplication. Because you are not taking the scalar multiplication by the numbers, you're putting the coefficient by the functions.
Yes.
That's one difference. And
Yes.
it's also very important to later that you should digest in your own way that so there are so many important like the concepts in this even this first page, but
Yes.
so
Yes.
you are using the so-called the Riesz representation
Yes.
theorem right after the orthonormal basis.
Yes.
So R plus of VU is defined by the inner products between V and U. This
Yeah.
is exact the place of using the Riesz representation theorem. And
Yes.
Riesz representation guarantees that there's no other like the choices rather than this form. This is what Riesz representation guarantees. So this is also super important. And for a moment, you might not feel comfortable with like the why ddx and ddy should be treated as a standard basis. This is the identification between the dual vectors, double dual base vector space and the vector space. So 1, comma 0 and 0, comma 1 in R2 is treated as just a vector space V, whereas ddx, ddy as so-called derivations, these are treated as a double dual space.
Double deal.
V star
Yes.
star. So like that. So that once you look at the linear algebra, like the contents that you will have a chance to look at it. Let's now
Yeah.
move on. So let's now move on to the page two. Okay, page two. So yeah, just here. So uh I personally think the most important differential form in any level is this example one. This is most important. So
Oh.
so because I'm lazy, so I usually just call it by so-called the winding one form. But
Find. Oh.
winding one form. If you try to visualize how it look like, so that just treat ddx as a 1, comma 0 and ddy as a 0, comma 1, then this v is just nothing but minus y, comma
Comma
x.
X. Yes.
So that if you draw the unit circle S1 in R2 whose center is at the origin, then you can point out how this vector builds uh like the would be like the behave so that you can easily see this is exactly tangential vector fields along the unit circle.
Oh. Yes.
along the unit circle. And we are now taking the vector field, so this is a winding vector field whatsoever, but the corresponding dual is we call the winding one form, winding one
Winding one
form.
form.
But there's a some like the simplification already in this like the example one in a sense that usually this is actually important like the simplification that we should like to recognize that there is actually the denominator given
Denominator.
by x squared plus y
Square
squared.
plus y square. Yeah.
So that in the unit circle, like the setting, this is now just already simplified, but this matters because the so-called the close one form, which is
Close.
not exact in
Which
general.
is not exact.
So if you just define this in the like the entire like the unit disk, including the origin, then this becomes actually this solves so-called the exact equation. Whereas if you take the puncture at the
Yeah.
origin, then you are not able to solve the exact equation. So this actually gives the our topological distinction so that it really matters whether or not we define this vector field on the either the like the unit disk or the puncture disk. This is actually the only topological difference. So that has a bunch of implications later on. So that it's good to think of it with what you today do. But yeah, I just want to point
Yes.
out this is important.
Yes.
And next one, yeah. Now let's look at example two. Example
Example
two.
two.
So here is I'd like to point it out the way
Oh,
to think.
yes.
So
Yes.
and this is a way to put the frame all together. Example two and example three.
Yes.
So there's yeah just to keep this like the page for a moment. So for example, so if you wanna do the elementary calculus for your observation, then I indeed love the setting right now that you did in a setting that so the ambient space is R3. So that you start from R3, it's very clear, and then just define the subsets accordingly. It doesn't matter if it becomes S2 or the torus. So start from R3, then you know how to describe everything so-called in terms of global coordinate. This is the
Global.
benefit of using the R3. If you start from R3, we know everything in terms X, Y, Z. Then just describe
Yes.
everything accordingly. We love
Yes.
it. So that's why we could do this computation. But when it comes to change the context, there are so many reasons to do that later on, then we'd like to throw these R3 assumptions away.
Oh.
So for example, when we learn Riemannian geometry,
Mm.
then we prefer to do everything in terms of so-called the intrinsic structure. Equivalently
Intrinsic,
speaking,
yeah.
we'd like to make everything only depends on the tangent space level, not the ambient space level. This is we call the intrinsic. So that we eventually want to throw this R3 assumption away, no matter what. For example, how we use this R3, then we can take the cross product. So that if we do not want to rely on the cross product computation, then we should like throw this R3 assumption away and we should recover the same computation without using R3. But still, as long as we are able to using the R3, then we love this. So for example, in the Riemannian context, I mean the intrinsic context, we should not use the cross product because that only works under the R3 ambient space assumption that we'd like to throw that away. So for example, so this like the S2 assumption, you use the computation in the area form. If you just go down the place you computed the area form of the S2, can you find the place? Area form of S2.
Product and then yeah.
Yeah, here. So that you can clearly see that we are using the cross product.
Yes.
So this works because we rely on the setting was in R3. But the Riemannian geometry do not assume such a like the assumption. This is so strong. So that you should like the from there should recognize how do we eliminate this cross product. Otherwise, we are not able to generalize because then we should like to stick with the R3 assumption otherwise. So for example, this is you can see that exactly same as if you start from the so-called first fundamental form that you know what are E, F, G, for example, right?
Yes.
Then this part is the absolute value of the cross product. This part is same as square root of the determinant or the E, G minus F squared. So then we can throw this cross product assumption away. so that it only rely on the inner
Mm.
products.
Mm.
So that R3 is no longer needed.
Mm.
Is that okay with you?
Yes. Oh,
Yeah.
that's
So
become.
yeah, let's just go back to that example 2 and 3 again. Yeah, here. So that when it comes to treat the Riemannian geometry contents, that we should think first just compute everything out in terms of R3 because this is handy. And then we should think after we finish this computation, how do we eliminate R3 assumption? Otherwise, we cannot do Riemannian geometry. So that we just prefer to call it by the preferring to get intrinsic structure. That's it. So, but let me also talk about the another like the context. When you wanna look at the algebraic structure rather than the Riemannian geometry, then you should change the assumption everything over C, not over real, over complex. That should be considered. So that you should like to take the bijection from S2 to so-called the CP1. By the way, CP1, you are not able to embed to the Euclidean space. That's not allowed. And for the torus, you should change this as a so-called elliptic curve equation. So the in the algebraic context, it's completely like they change everything in terms of the like the describing the same amount of the information. But what you can still believe is you still have the explicit bijections. So that as long as you are able to describe everything in R3, there should be way. For example, we can throw this R3 assumption away eventually in the explicit computation level, and you can also throw this like the over real assumption also away. So that in that like the level of the transferring everything, then you can see so what was really happening here. For example, torus is changing as what? Y squared equals x cubed plus x plus b. It looks kind of like the mysterious for a moment how the torus should be like that. But what you should believe is what you did this computation under the R3 assumption can be transferred in terms of the elliptic equation, for example, y squared equals x cubed plus x plus b. So then you can do exact same computation. So, but change the context. So that's why we start from this like the simplest possible but elementary, never trivial observations in the first place. In a sense that we can now later see how that abstraction really like to pop up all of a sudden. So that's I wanna also point it out. But yeah, this computation is super important. So now let's just move on for the line integral as integral of one forms. So it is important to recognize the spirit of the integral of the differential forms, not only restrict to the one form, also works for any forms, is because we'd like to use the change of variables. That's it. So in the vector field level, it depends on the choosing the coordinate, whereas in terms of integration of differential forms, it does not depend on choices of the coordinates. So that's why we prefer to use the forms rather than the vector fields. So, but you can do the following because in the explicit computation, you should fix the coordinate. There's no other way. So that in the explicit computation, you can do whatever you want. And the differential form is just nothing but the description in the abstract, like a formalism. So, so again, when you need to compute the quantities explicit, then you should fix the coordinate, then you can get the quantities. Then in that level, actually, you are dealing with the vector field as you compute everything actually in terms of vector fields, right? But in the formalism, but then the formalism level, we do not want to rely on the choices of the coordinates or the local coordinates. Then we want to describe accordingly. That's the what we call line integral as integral of the one form. That's it. But still, it is most like the important like the one form is the winding form in many like the with many like the reasons. So let's just move on to the page 5 that you put by own comment. I know he just quit, so he might just come back. I also wanna point it out for a moment that yeah, why he's not here? Mm, so far, before U might rejoin. So any questions or comments? So, one context I'd like to share without U is so the most important, like the one form is DZ on the complex torus. So DZ, so on the complex torus is global holomorphic one form because complex torus can be defined as a C quotient out by the rank 2 lattice so that the Z coordinate from C can be descend to the torus globally. So what I'm saying is that then DZ can be descend also globally as well. So DZ is from one form, whereas CP1 level, DZ cannot be never holomorphic. That's not possible. So this is important, like the distinction in Riemann's mathematics also as well. Yeah, ooh, so it seems to have some connection
Oh
issue.
yeah, I'm sorry. There was a connection. Sorry.
Sure. So can you re-share your screen?
Yeah, one moment. Because my laptop is dead. The battery's out. So one moment, please.
Sure.
Can
All
you
right.
can you
Yeah,
can you
so
see my note?
can
Yeah,
you,
yeah,
yeah, we can see your screen. So can
yeah.
you go to the page 5?
One, two, three, four. Yeah. Yes.
Yeah, here. Yeah, page 5. Yeah, here. So, so here is I want you to drill because in the master study of your own, I'd like to
Yeah.
say so that you should
Yeah.
know how to reduce what we are doing in terms of the information of differential equations.
Mm,
So differential one form correspond to so-called the exact equation. Differential
yes.
two form correspond to the so-called Poisson equation that you already saw.
Yes.
So that
Yes.
not knowing this as in the conceptual level, you should know how
Mm,
to reduce each.
yes.
So the topological distinction of S1, S2, and T2 can be distinct in terms of looking at the information of the exact equations. So, for example, S1 level, so not as R2. So in the elementary differential equation class of the undergraduate, so differential equation is solvable. So when we start from so-called mdx plus ndy equals 0, then that satisfies the D-close assumption or the exactness assumption, then you are always able to solve it as a du. Whereas in the S1 level, because of the winding form, you are not able to solve the exact equation. So I highly recommend you to just resolve the differential equations, exact differential equations for reviewing yourself. And then you need to
Yeah.
see why the winding form explain, justify we are not able to solve the exact differential equation. That's the
Mm,
place of using the S1 first. And for
yes.
whereas S2 is not like that. So that S2 is the so-called the one-point compactification of the R2. In the R2 level, in any like the ball of the any radius, you are always able to solve the exact equation. Then if you just expand that like the ball, so towards to the point of the at the infinity, so there's no topological obstruction of solving the exact differential equation. So S2 exact equation is always solvable. But torus can be defined as so-called S1 cross S1. So you are able to describe the bijections from the embedded torus in R3 and S1 cross S1, find the bijection accordingly. Then
Yes.
because of the effect of the S1, you can find there are two, later we will call this a so-called homological cycle, two homological cycles that we are not able to solve the exact equations. But so in terms of the solving Poisson equation, S2 and torus, there's no distinction. So later this would be like the formulas as a like the Bayer theorem or whatsoever. But
Oh.
so S2 and torus like the level. So solving the Poisson equation is just the same. It is actually the same for any compact orientable surfaces. But
Mm,
the solving the exact equation is different. So what
mm,
I'd like to study is just a just look at the exact information, exact equation, just the
Yes.
information in the level
Yes.
of S1, S2, and torus, and there should be the
Yes.
distinction. Then
Okay.
you can see how the
Yes.
like the abstraction and formalism works accordingly. That's what I want to point it out. And at the same
Yes.
time, this like the page is also important. Green theorem, Stokes theorem is to just revisit the fundamental theorem of calculus, one variable like the level. So
Mm,
I'd like to, so again, I really appreciate what you put the effort, but you should like the try to drill as concrete as possible in order to reach out to the one variable fundamental theorem of calculus in the following like the
mm,
sense. So for
mm,
example, you can just take Green's theorem as a fact to apply as a just a computation like the package. You are able to do it for sure. But Green's theorem is just nothing but the consequence of the fundamental theorem of calculus. I'm talking about the one variable. So that
mm.
we
Yeah.
should not treat that as a separate pieces. This is the
Mm,
important point. So the importance of the Green's theorem is the following. So if you just look at the statement of the Green's theorem. So next page. Here, yep. So this is what usual the general textbooks are talking about, but I do not actually
yes.
like this form.
Oh.
I just
Ah.
stick with this like a page for a
Yeah.
moment.
Yeah. Yeah.
So because if we take for example like a heart like the like the type of the
Mm,
surface, we have
yes.
no idea how do we connect with the one variable fundamental calculus.
Mm,
So the way to do is the following. So just take the square perfectly ideal square. So just draw R2, draw the square. Then there are now four like the edges there that you can apply fundamental calculus four times. Is that clear? Four times.
mm,
Then that becomes a
yes.
green theorem. That's it.
Mm, mm,
Just a double check. And then this like the form of changing the surface from the square to the like the any like the generic form is coming from the curve-free condition. Or it's the same as solving Cauchy-Riemann equation later on. It's just a curve free, curve equals zero. And just using this like the green theorem so that we are allowed to change the form of the surface because the integral values are the same. That's coming from the curve is just a zero. So
yeah.
that we are now able to change the form from the square to the any like the surface form accordingly. But this is just nothing but one variable calculus. That's
Mm,
I want all participants check by yourself. This is important. What about the divergence theorem? This is a one dimensional higher. Same divergence
mm,
theorem. Just to make the perfectly like the perfect like the cube first, and apply the again fundamental theorem calculus for each of the faces. That's it. So what we only rely on is just nothing but the one variable fundamental theorem calculus. This is important point. Then, like for example, the like the changing the deform the shape of the like the cube is again just the same, so that we just can do it because the integral values are not changing. That's it.
mm,
So that in the concretized level, you should really see that all we know is nothing but one variable calculus. But why we call by so many different names of the theorems? Because it is like preferred to distinguish each of the settings first of all, and eventually it's just nothing but just we'd like to say we want to choose the any coordinate that we'd like to work on. For example, we'd like to
mm,
treat S2 as in R3. We can treat S2 as a like the CP1. We can treat like the S2 as also different form, whatever we want in our own context. Then in order to do it, we should treat as a integral of the differential form rather than the integral of the vector field. That just means that we want to just play with any coordinate that we prefer. That's it. But
yes.
calculation level, all we just do is one variable calculus.
Mm,
This is a
yes.
really, or others just putting the name of it in the abstract like formalism. So
Yes.
this is I want to point it out. And if some of the participants already studied the complex analysis, then curve-free condition is equivalent to solve the Cauchy-Riemann equation is equivalent like the information, or in terms of the exterior derivative, it's just a declosed condition. It's just the same. So that's why complex analysis use the Green's like the theorem a lot, but this is our reality. And it's just the same as just saying the vector field becomes a holomorphic function. So it's all
Mm,
same information. It's
mm,
not the analog. It's just a way to just use the Green theorem is what I want to point it out. And so let's just now move on. So the wedge product. So let's now move on to the page like the 10. Yeah, here. So this is coming from the 2 by 2 matrices determinant. So that if you think about the determinant, so I'm just talking about
So,
the
I'm sorry. I'm sorry. Oh, you meant this came from determinant of two matrix?
determinant of 2 by 2 matrix.
Um,
So that if you
okay.
change the either the place of the rows or the place of the columns, then we know we should change the sign. That's it.
Yes.
And if we have
So
a
that's the
two like the
definition.
parallel
I'm
vectors,
sorry.
then it should be zero.
Yeah. Yeah.
So
I mean,
the
yeah.
mhm.
Mm.
So
I'm sorry. Yeah.
the intuition, because I wanna like reduce our intuition in each of the participants in the level of the you are able to do the computation, getting the quantities in the very like the easy way. So that putting the wedge product just means so just a dx or dy, it's either the co-vectors or the vectors, right? So treat that as a n tuples. That's it. And then
Mm.
what's the meaning of the putting the wedge product? Make the determinant. That's it. So for
Mm.
example, dx and dy in this context, those are just nothing but vectors in R2.
Mm.
Then putting the wedge product, what is it? It's just a determinant. dx for the first row, dy for the second row. What about dx wedge dy with dz? Then each dx, dy, dz are vectors in R3. Then just put each of the rows accordingly. That's it. So it's just using the just a determinant. That's all we have. It's so
Mm.
simple.
Mm.
Then if you that with this perspective, you just investigate the properties, it's the same as the coordinate like the change and just deal with the property of the determinant. You might remember that if you the determinant also behave as a so-called group homomorphism, so that if you just put like the A times B and put the determinant is determinant A times determinant B, it's all we use for that. That's all we use. And
Yes. Yes.
determinant is independent to the choices of the basis. This is also we rely on for computing the differential integral of the differential forms. So our reality is just nothing but the determinants. And
Mm.
when it comes to deal with the determinants, so there are two different like the levels of describing the same information. One is in terms of the like the algebraic like the description. We have the like symmetry group, and we have a like the sine or signum function, and there's a odd permutation, even
Mm.
permutation, and we have a algebraic description. That's one like the description of a determinant, and another
Mm.
description is sign volume. That's it.
Mm.
And
Yes.
algebraic side and the geometric like the side just explain actually the same object in a different like the feature, but it's just same.
Yes.
So that's why
Yes.
the wedge product is to make the signed volume. And in order to talk
Mm.
about this signed volume, then we need to fix the order of the standard basis. For example, so we should like to think of so for in R2 level, E1, E2, E2, E1. So how do we
Mm.
distinguish? So if you just call volume of the E1, E2 is 1, then volume E2, E1 should be -1, something like that. Because we
Ah.
change the order in the level of the determinant. But
Mm.
there's no way to just use for everyone to use. Well, E1, E2 should be the answer. How can one claim that? We are not able to do that. So that's why we put the orientation assumption for that.
Mm. Mm. Okay.
So this is our reality. So
Mm.
that just the next like a page, all you can see is just we are using the property of the determinant of the in the 2 by 2 matrix like a level. So that's what
Yes.
you can like to point out. Of course, in the computation that would check is exactly what one should do. So now let's just move on to the very like the last page,
Oh, yes.
very last page. So let's just look at one by one. So in the S1 level, so minus y dx plus x dy integral value should be 2 pi. I cannot agree with that, but S2 level, it should be 0.
Oh.
Because
Mm.
getting the 0 value is equivalent to say exact equation is solvable. In S2 level, it is solvable. So they must be 0.
Oh.
So that in the computation, you should get 0. Otherwise,
Okay.
either known theory is
Mm.
incorrect, then you are able to write the paper because you can against the known theory if this value is in the
Yes.
2 pi.
Yes. Okay.
So 0 is nothing to do with the area form. 0
Yes.
value is the integral of the curvature to form or the with the Gaussian curvature.
Yes.
So if you compute the area to form and the integral, it cannot be 0.
Mm.
It's not the Euler characteristic. So if you
Yes.
take the
Oh,
integral of the area. You should get the area. Area cannot be zero. This is different from
yes.
the Euler characteristic. So it cannot
Oh,
be
yes.
zero.
Oh, yes, yes, yes. Oh,
And in the S1 level, there is no genus.
yes. No.
And genus equal one is nothing to do with the computation of the area to form.
Oh, yes.
So this, like the genus, can be captured by looking at the winding form in the level of the S2 and the torus, in a sense that in the S2 level, you are not able to make the integral of the minus y dx plus x dy over x squared plus y squared to be non-zero value. That's not possible. If you are able to do it, this will be published in the Annals of Mathematics. If you are able to do it. This is really like the astonishing result if you are able to make such a like a claim. And in the like the level of the torus, so this g equals 1 is coming from each s1 like the cycles, and you are able to find two cycles that you are not able to solve the exact equations that can be check explicit. But I really like to appreciate your like effort again. And this is the way of the spirit. So why we rely on this computation, then now you can, so I'm not trying to point it out the errors from my own like the knowledge. Now this
Yes.
becomes a mathematical science so that we have
Yes.
some conjecture. Most of the time conjecture should be wrong. That's the
Yes.
spirit of the doing mathematical research. Then we
Yeah.
are not give up from there. So still
Yeah.
there should be some important like the interesting observations out of it. Then
Yeah.
if you try to push further, then there must be something new that people were neglected before, but you are able to do something. Then you are able to
Yes.
abstractize, and that's the way to the math research.
Yes. Yes.
Yeah. So any other comments or questions for now?
I wonder, what, so, uh, the vector field, that will calculate in torus, this is, uh, there is no meaning, or I wonder this, I think, this calculation should be zero, for both of sphere and torus, because of your explanation. So we can check, next time. Anyway,
Mm.
uh, the uh, there is no meaning, or
So you can think this way. So let me try to visualize my own explanation, but this can be realized in terms of the explicit elementary calculus computation. So for example, think about this S2. So
Yeah.
S2, just make any like the loop, any loop.
Mm.
Then you
Mm.
can just contract to make it
Right.
to be the one point, single point that can be continuously deformed to, so as long as you just make the loop on the like the two-dimensional sphere, then you're always able to make that to be the just a single like the so it's a singleton set. So topologically, this is called so-called a simply connectedness.
Mm.
So, but this is kind of clear in the like the way of thinking that if you, for example, think about the R2, for example. R2, if you start from any loop, then you are able to deform continuously to the towards the single point, right? The
Yes.
sphere, two-dimensional sphere is we just add additional one point. So it's just the same feature. So
Yes.
that is the equivalent to say, so if you start from the winding form in the R2 level, this is solvable in terms of the exact equation so that there's no like the puncture effect so that this is solvable. Is that clear? Because there's no effect of x squared plus y squared in the denominator. Whereas in the torus like the level, there's a this loop and this loop that you are not able
Yes.
to deform continuously to the towards the single point. That's not possible. That's not allowed.
Yes.
So that
Yes.
for this one, even it satisfies the exactness, like the d close assumption, which is this correspond to the exact equation, you are not able to find du. Though there are commonly like the level. That means you are not able to make it to be the exact. This like the d close one form, winding form cannot be realized as a du. That's not possible. That's not allowed. Equivalently speaking, exact equation is not solvable for this loop and this loop. So this like the vector field is nothing to do with either this one nor this one. So that's why the integral value is zero. Because by the way, this is also important like the observation that if so, actually general theory says that if this uh, surface integral is 0, actually this is solvable. And solvability is equivalent to get the integral value is non-zero. If it is 0, it's solvable. If not, non-solvable. That's it. So that's why. So he just select the vector field in his form like the intuition. So and it just becomes 0. So it just turns out to be just nothing to do with the topological distribution. It's just a computation. So, but this is so natural. So because otherwise, how can we reach the interesting like the like the quantities, right? This is the natural like the procedure rather than learning something from the first place to just get it by just looking at the known references. This is the spirit of the doing the experiment. So in that way, I love it. And by the way, so the setting is also wrong in page like the 16. So the
Yes.
so here, so
Yes.
now this is the embedded torus in R3.
Yes.
You should not work with dx by dy. You ignore dz.
Oh, yes. Oh, yes.
So you take the slice completely so that so you ignore all like the z components. So that's why the computation is not that interesting. You should reflect the structure of the embedded torus, meaning that you should also reflect like the dz.
Yes. Yes. Oh, thank you. Yeah.
But yeah, again, this is not the giving the critic. This is just the I
Yeah,
love what you
of
did.
course. Yes. Yeah, of course. Yeah. Thank you.
So any other comments or questions? So because there is one scheduled additional presentation, but I actually
yeah.
want to stop today
Oh,
or in terms of
yes.
presentation, but I'd like to just invite the spirit of the each of the presentation from each of you in a way that, but yeah, let me share my own screen and try
Yes.
to invite what you from now on, each of you to work on. So for any presentations with the any topics, I'd like to reduce to the level of the S2 or the torus in this like the level we presented today because so others are just nothing but the reinterpreting of what we did today. And what today we did is we can concretely figure it out what was going on. Then others are just nothing but the mathematical formalism how to get that. So this is not mandatory for all the participants, but so if you want to work on the geometric part by using calculus, so there is a standard name of it. We call it by what? Riemannian geometry. So this is what my advisor taught me when I was a graduate student. So by the way, my advisor will come to Texas State in coming November. I'm very thrilled to like to have him to introduce you guys in person. I'm actually really looking for that. So my advisor said that after learning Riemannian geometry from the graduate class, 95% of graduate students still do not know how to do the calculus concretely. They just don't know the conceptual level. They do not know what to do. So that's why that I wanna the real, at least in the level within my team, that you guys, if you wanna claim that you learn Riemannian geometry in your like a graduate school life, I want you to know how to bridge between the elementary calculus and the abstract concept of the Riemannian geometry through this seminar. So that the way to learn would be the following. So as I already shared, this file through the Discord channel is I just make the problems that at
Yes.
least I can do without looking at any references by myself. And at least I am very clear that once you know how to do each of the computations, then this will be used for each of the problems will be used more than 100 times, in my personal opinion. So what I want you to work on each of the seminar would be the following. So if even you can just bring this without any preparation, you can just suggest that why don't we work on this problem this week? Then for example, now we know how to do this.
Oh, yeah. Yes.
Is that clear? But we made a mistake on the torus.
Yes.
Is that clear? So that now we can exactly measure whether or not we successfully solve some problems or not,
Yeah.
because this now is the not the interpretation level or conceptual
Mm-hmm.
level, but there's
Yeah.
a concrete like the answer in terms of the quantities and the computations. So that, for example, like this, so that we know or know gradient in R2.
Mm.
Conceptually, you already have the intuition regarding the gradient of S2, but you still do not know how to do it by yourself.
Mm.
So I just want to go over one by one in a way that, so for example, if any of you suggest, so why don't we discuss this problem this week? Then not rather than just looking at one possible like the computational method, so each of us just bring our own method. For example, in the S2 level, some of you might want to use the stratigraphic projection. Some of you want to use the like the coordinate of the CP1. Some of you want to use the like the embed like the S2 structure and so on. And the way to compute could be all different, but in terms of quantity, it should be all the same. Otherwise,
Yes.
someone must be correct or incorrect simultaneously, right?
Mm.
So in that way, so by end of this year, so for the doctoral level students here, so if you wanna do the your own research within Riemannian geometry world, I want you to work on that step by step. But if you do not have to do the Riemannian geometry research, so for example, if you want to complete like the ignore that part, that's completely fine. Then you can just directly jump into SCP-1 and the complex torus to just look at the corresponding just a part of the what is the main meaning of the taking the derivative. That's just nothing but the maximal idea quotient by maximal idea. So what is the meaning of the like the integration? So from the Riemann rule theorem, it's just nothing but the alternating sum of the Betti numbers, for example, like that. So that you do not need to rely on the Riemannian geometry computation, but it's completely up to you guys. But if you want to claim that you know Riemannian geometry, I force you to not know the conceptual level, you know how to do the computation. Then my like the necessity would be, so I will force you to do all those problems one by one. And if I have a chance to teach graduate level Riemannian geometry in at Texas State, this would be the probably final that I will force all graduate students to submit later on.
Mhm.
So, and also the final presentation with the each of the topics presentation also as well. So this could be good like the preparation for that if you want to take that like a course later on. So that's what I want to like to claim. So that so the presentation from incoming like the so from next week would be the following. So any of you can suggest, so we'd like to drill this problem this week, for example. Then each of you can just think of how to solve that problem by your own. Then we will just discuss about that problems. By the way, it can be just a repeat for the interesting problems, for example, so that if any of you, I'd like to just work on this problem more detailed, then so each of you just bring your own like the ideas and just discuss accordingly. So except for that, I will just also ask each of you like free presentations regarding your own like the research like the topics. Then we so but the way of the presenting is you should like to reduce the level of the calculus on S2 and torus so that without even knowing the abstract like the formalism, still every like a participant can catch up what was going on here. So that's what I wanna say. So any questions or comments before we finish the seminar today? Alrighty, then we can stop the seminar today here. And again, well, I know how like the getting the pressure of like the changing the style and learning the mathematics this way. I know how it like the feels like. So how do I really do this without knowing the like the necessary like the knowledge that I should know? So, but this is the way to do the mathematical research. You already reached out how to start the mathematical like the science that so again if you can show the minus y dx plus x dy is non-zero in the level of the S2, then this is very astonishing, but that cannot be done. So that
Yeah.
in that way, so that you can really make some interesting conjecture and you can really understand some pieces more detail rather than knowing the conceptual like the level. So this is
Yes.
what I want to point out and very
Yes.
like a well done. So if you have any comments, you can put it and we will stop the seminar today.
Yeah, first of all, I'm very grateful for your advising and guideline. And yeah, I just changed my mind. So always computation examples come first before concept or definitions and theorems and axioms. You might don't want to just list up like definitions first. You should just dive in like, I'm gonna get this value. I'm gonna computation this. I'm gonna get this result. That's the speed. Yeah. Thank you. Yeah.
Yeah, before we finish today's seminar, I just want to show you just a one last one for today. I'm not sure I can show you immediate, but I think I found it. Just hang on a sec. So, what I teach all of you would be quite like the stupid in a way that not giving you the like the advanced level of the topics to teach. I just explain how important to put emphasis on drill the calculation or elementary calculus detail. That's what I pointed out. So for example, I love to do the math research in geometry and topology basically. So I do like to understand the mathematical structure from geometry and topology point of view, but all I can do is just a calculus. And geometry and topology is talking about the symmetry of the spaces that we are interested in, for example. Then how can we do the research? So I'd like to show you my own like the dissertation, how stupid I am. So let me show you for that. So for example, so this is my dissertation that I don't even like to post on the website because I feel shame of myself. So if I just go back to the last like the appendix side. So this is my own computation of the curvature. So for the complex dimension 2, so this is real dimension 4. This is my meaning of the curvature up to here. It's not that long. So from here I can see the meaning of the curvature. Where was it? So let's just count the numbers of the page. So 1, 2, 3, 4, 5. Once you reach out up to here, then you can really compute the quantities of the curvature in the complex dimension 2. For complex dimension 3, this is my meaning of the computing the curvature. Once you reach out up to here, then you can genuinely see the quantity. And in my own experience, so I used a supercomputer at University of Connecticut. It took 40 hours to really see the genuine quantities. And I don't really believe after I do this computation with two publications that people are talking about the curvature and the implication. I don't really trust what they are talking about because computing even the complex dimension 3 case of the differential geometric quantities is barely possible, truth be told. So that if they claim that they know something rather than the perfect like a symmetric space, such as like the CP3, something like that, I don't really trust they really look into what they should. So meaning of the symmetry, for example, for me is for those like the list of the quantities from the iteration in the like the quantities, most of the values are just zero for CP3. But for interesting spaces, there are some non-trivial effects that still I do not know how to interpret what that means. That's the meaning of the doing math research, right? And that's the way I write my two papers out of it in a way that just compute the curvatures with interesting spaces. And there are certain quantities I have no idea. And if I just look at those elementary spaces, all those like the interesting quantities just become zero. So that I do not have any interpretation. Then I still do not know what to do. Then I made some of the like the conjectures from my computation that I brought that to my former advisor. He also liked what I observed, but none of us are able to prove anything interesting out of it. That's the my way of doing the research. Then what else I can formulate the statement by myself? Because we first need to get the observation. But in order to make the observation in the qualified like the way, then you need to qualify your own like the experiments. How do we make the qualified like the experiments? Your computation should reach out a certain level of the qualities. What does that mean? So if your computation is exactly the same as what like the AI tools are talking about, it's not qualified, in my opinion, as like the Garen is now pointing out, right? So if you just ask the the question to the AI without the specified like context. Those computations are so I should say most of the time it could be just a bullshit, should be told. So that you should like the redesign the calculation or like the experiment in a way that you can like extract the interesting information by yourself. So yeah, it's just the time extension. But yeah, Karen, can you just share your own context? So if you have experience of doing the computation with your own way, what did you experience, and so what did you get out of it? So, Karen, can you just share anything if you have?
Usually they're not, they don't approach the computations in a mathematical way. I think that they sometimes give you good answers, but when you make the computations harder, they don't have the mathematical foundations really to give you the correct answer. The computations you put in your supercomputer at UConn will not be able to be done by an LLM yet. Not possible.
Yep. I cannot agree more. Not possible. Not even close. So, and from there, you can find which problem is interesting. So if that can be solved by just an LLM with just certain small like the amount of logic, that's not interesting. So that if you try to compute that out by yourself, you can first like realize this is almost not possible. But if you just reduce the computation in very like clever like the tricks, that's the spirit of doing mathematical research, right? So it looks almost like impossible in terms of amount of the information, but you can use the symmetry to reduce the computation. Then the trick is like a very like the deserve to get published somewhere. So this is the spirit. All right, so let's just stop here. And I again appreciate U's contribution this seminar. And now you guys understand how to prepare this seminar for your own. So let me stop here.
Thank you.